The general idea when multiplying fractions is to multiply straight across. We multiply numerators times numerators and denominators times denominators, and we don't have to worry about finding common denominators. So it's a pretty simple process by comparison to adding and subtracting. Here, if we're multiplying 2/5 times 7/3, it's just 2 times 7, 14. And then 5 times 3, 15, and the answer is 14/15. Now many times we'll multiply straight across like this to kind of emphasize the idea of multiplying numerators times numerators and denominators times denominators, but you know that from the past that this answer can be put under this expression and it would be just fine. Now the word of means to multiply, and of course when we use the word product it means to multiply as well. But when we say 1/3 of 2/5, it means 1/3 times 2/5. And I want to emphasize that idea very quickly. A lot of times when fractions are involved, the word of comes up in certain kinds of word problems. So 1/3 of 2/5 means very simply 1/3 times 2/5. And we multiply going straight across. 1 times 2, 2. For the numerator, 3 times 5, 15. 1/2 of 1/2. Half of a half, you see, half of a half means 1/2 times 1/2. 1 times 1, 1. 2 times 2, 4. Half of a half is 1/4. Consider this problem. We're multiplying a common fraction, a proper fraction like 1/4, times a whole number 5. And to accomplish that and to get the idea of numerators times numerators, denominators times denominators, we need to write this as a fraction. We'll write it as an improper fraction, and it's written as 5/1. So we just change this to this form. Think of it like this, and now multiply straight across. 1 times 5, 5. 4 times 1, 4. 5/4 will become 1 1/4 as a mixed number. But the idea when you're dealing with a whole number and multiplying in this world of fractions is to think of the whole number over 1 for proper multiplication. Now here's a kind of a special case. We're multiplying 2/5 times 5/2. Notice the structure of the two fractions. It's kind of like this fraction is just flipped over for that fraction. And when we multiply, we get, well, let's see, 2 times 5, 10. Over 5 times 2, 10. 10 divided by 10 is 1. So this becomes 1. Now this special arrangement of fractions has a name, and the name given to each of these fractions when compared to the other is reciprocal. That is, 5/2 is the reciprocal of 2/5. And it's also the case that 2/5 is the reciprocal of 5/2. It's just the same fraction but flipped over. That's a good way to think about it. And every time reciprocals are multiplied times one another, we get 1 as the result, because after all, we get this idea that we have a number over itself, which becomes 1. So this is these are reciprocals of one another. They're also called multiplicative inverses of one another. Multiplicative inverses. You see, it's that special fraction partner that we can multiply and get 1 with the result. Now let's think about reciprocal for a moment. Let's write the reciprocal of 4/5. You see, the reciprocal of 4/5, oh, that would be 5/4. You see, just flip the fraction over. The reciprocal of 10/7 is 7/10. Just flip it over. That's all there is to it. We're not paying any attention to whether it's an improper fraction or a proper fraction, you see. Just flip it over. The reciprocal of 4. This doesn't even look like a fraction. But we can write the reciprocal by thinking about 4 as being 4/1. So the reciprocal is 1/4. Now, here's another situation involving fractions. We haven't really talked about situations where fractions are reducible or answers turn out to be reducible. Here's an example of that situation. If I'm multiplying here and just going straight across, I would have 3 times 4, 12 for the numerator of the answer, and 8 times 9, 72 for the denominator. But notice that 12 and 72 are both even, and therefore we can certainly reduce. We may be able to reduce by more than just that common factor of 2 in the numerator and denominator, but at least we can start there. Now, there are a couple of ways of thinking about this reduction process. The most complete way to think about it would be to write a prime factorization for both the numerator and denominator and just eliminate like factors that appear in the numerator and denominator. But a way to do it would be like this. We could say, oh, well, wait a second, we can write 12 as 2 times 6. You see, and we can write 72 as 2 times, well, let's see, 2 into 72, oh, that's 36. You see, and the 2's go out. And then you would notice, oh, we have 6 over 36. Well, 6 divides 36. That is, we can think of this as 6 over 6 times 6, and this 6 will cancel with that one, and we're left then with 1/6. Now, that's a pretty good way to do it. From the very beginning, though, we could have reduced like this. Rather than sort of make the separation of factors and then show the cancellation, we can reduce like this. We can say, well, I see that the two numbers are even, and therefore 2 will divide both of these. 12 divided by 2 is 6, and 72 divided by 2 is 36. And now we look at the 6 and the 36. You see, and we say 6 into 6 goes 1, 6 into 36 goes 6, and we arrive at the 1/6 as expected, kind of like this. Now, there's even another way to approach this problem. Notice that we had all of this cancellation business after we arrived at an answer of 12 over 72. Could we have performed some of this reduction business before we even arrive at this step? And the answer is yes, that in the original problem we can perform some operations that will allow us to reduce, and that situation goes like this. It turns out that if we have a factor in any numerator that kind of matches a factor in a denominator, we can eliminate those factors right up here. And it's called cancellation. And all we're doing is canceling like factors in numerators and denominators. So here we can accomplish that cancellation like this. And again, there are a couple of ways of doing this, but the most complete way to look at it is like this. That in our fractions, this is 3 over, and I'll write 2 times 2 times 2. I'll use prime factorizations here just for emphasis for right now. 4 is 2 times 2. And 9 is 3 times 3. You see, and now we have, let's see, this 2 will cancel with that 2. And this 2 will cancel with that 2. And this 3 will cancel with that 3. And now all of the factors have been canceled in all of these numerators. And what's really left, though, is 1's in their place. And it's kind of like 1 times 1 times 1 up here. But the idea is that everything cancels, so we're left with 1 in the numerators, and in the denominator we have 2 times 3, 6, 1/6 as expected. Now, another way to approach this cancellation idea and to get rid of these factors that we see here is to look at the original problem and just look for those cancellation opportunities between the numbers that appear up here. We say 3 goes into 9, you see, so 3 into 3 goes 1, and 3 into 9 goes 3. And then the 4 and the 8. 8 is a multiple of 4, so 4 divides 8 evenly. So we say 4 into 4 goes 1, 4 into 8 goes 2. And now multiply the leftover factors as the smoke clears on all of this cancellation. So we have 1 times 1 is 1, and then 2 times 3, 6. So this is really the fastest way to approach the situation. Let's look at it again, and this time we have one of the fractions is negative. One's negative and one is understood to be positive. Now, this business about multiplying with fractions carries the same rules that we talked about involving integers. That is, if we're multiplying a couple of fractions and one of them is positive and the other negative, then the answer is going to be negative. It doesn't matter which one's larger or smaller and all of that kind of thing. Just like with integers, if the signs are different, we get positive answers. If the signs are the same, if the signs are different, we get negative answers. If the signs are the same, we get positive answers. Here the signs are different, so we're going to get a negative result. So we can just write that down at the very beginning. Now let's look for cancellation opportunities. I see that 3 is a factor in 15, and 3 appears up here. So I can cancel this 3 with the 3 which is in 15. And I would say 3 into 3 goes 1, 3 into 15 goes 5. And here with the 4 and the 8, same idea. 4 into 4 goes 1, 4 into 8 goes 2. Now when you're dealing with fractions and you're setting it up like this, and you're working your problems, be sure to give yourself enough room above and below the fractions that you're multiplying so that you can show the cancellations and the numbers that are left over, the leftover factors, so that if you ever want to come back later and check your problem, you'll have all the evidence here to either discover that you've done it correctly or that you have made a mistake. But at any rate, negative times positive negative, 1 times 2, 2 for the numerator, and 1 times 5, 5 for the denominator. Negative 2/5 is the answer. Here we have 3 fractions to be multiplied, and we can think about, well, gee, we can associate these 3 factors any way we'd like, so we can multiply any 2 of them first if we want to, but let's just multiply all 3 of them at one time. Now consider the signs here. We have a negative fraction here, a negative value here. Negative times negative would be positive. An even number of negative values, you see, give as a result a positive answer. Now let's look for cancellation opportunities, and we can look for those opportunities between any numerator and any denominator. That is, this 3 can cancel with the 3 in the 9 down here. So 3 into 3, 1, 3 into 9, 3. And now let's look for others. Oh, good, we have the 4 and the 8. 4 into 4, 1, 4 into 8, 2. And oh, happy day, we have another one. We have 2 into 2, 1, and the 2 into this 2, also 1. Now, everything is cleared out of the numerator, so we're pretty much done here with our cancellations. 1 times 1 times 1 is 1 for the numerator, and 1 times 1 times 3, 3 for the denominator. So positive 1/3, or simply 1/3, is the answer. Suppose we want to find the product of these two numbers. Notice they're mixed numbers this time. We're moving from regular fractions into mixed numbers. And when we have to deal with mixed numbers in this multiplication process, we change them to improper fractions and then just multiply straight across as we normally would and look for those cancellation opportunities. All right, let's do that here. We know that product means the result of a multiplication problem, and we're given the 2 factors to be multiplied here. So what we're really doing is taking negative 4 and 1/6, and we're multiplying times 2 and 7/10. Did you notice that I hesitated a little bit? We're using the dot here for multiplication. I was thinking about using parentheses. Either one of them would be just fine. Now, we want to change these into improper fractions, so this becomes negative, let's see, 6 times 4, 24, and 1, 25. So this is 25/6, and we're multiplying times 10 times 2, 20, plus 7, 27/10. And now we're looking for cancellation opportunities. And here's a situation where if I had it to do over again, and if I were doing 3 or 4 of these, I would have left myself more room right here. You see, I jammed myself a little bit on the cancellation business. Let me show you what I'm talking about. When I try to cancel right here, I see that 5 is a factor in 10 and 5 is a factor here. I go 5 into 10 goes 2, 5 into 25 goes 5. And this 5 is jammed up into that other part of the problem. If I'm going to organize things correctly, and we want to emphasize that here because organization is so very important as the problems become more and more complicated. So it's important to think about that idea actively right now on the simpler kinds of problems. So we want to amplify the organizational skill idea. All right, so here we go. Now I'm going to rebuild what we had before. We have a negative value here. Notice I'm just dropping down farther. 6 times 4, 24, and 1, 25, 6. All right, and then over here, 10 times 2, 20, and 7, 27/10. And now let's cancel. Well, let's see. The 5 into 10 goes 2. 5 into 25 goes 5. And now this 5 isn't jammed into that other number. All right, in a similar way, let's see. We have the 6 and the 27. 3 will divide both the 6 and the 27. 3 into 6 goes 2. 3 into 27 goes 9. And I'm looking for other cancellation opportunities. I don't see any. Negative times positive is negative. Multiplying straight across, 5 times 9, 45. And 2 times 2, 4. This is a highly improper fraction, so we would change it to a mixed number. Let's see, negative 4 into 45. Now, it's perfectly all right in changing this to go over and actively go through the long division process. There's nothing wrong with that. Some of my students in the past have thought, you know, they'll think to themselves, And I ask them about this later after I see what they're doing. They're scribbling on the side and all that kind of stuff. And I say, why did you scribble this? And they say, well, gee, I'm supposed to know how to do this. I should be able to do this mentally and all that kind of stuff. And it might indicate that I'm not as smart as I could be if I go over and show the work on the side. That is completely false. That is completely false. You show more organizational skill, more care about what you're doing by showing the work and illustrating what you're doing to get your answer. And that's a very, very important thing to get straight here at this point in your mathematical career. At any rate, okay, we have 45 divided by 4, so it's okay to come out here to the side and say 4 into 45. Let's see, 4 into 4, 1, 1 times 4, 4. Subtract, we get 0, bring down the next digit. 4 into 5, 1, 1 times 4, 4. Subtract, we get 1. So it's 11 with 1 as the remainder. And we'll write this as 11 and 1/4. So negative 11 and 1/4. Now another way to get at it is to say 4 into 4, 1, you see? And then 4 into 5 goes 1 with the 1 left over. So negative 11 and 1/4, either way you look at it. Here we have 7x over 12 times 4y, and this is kind of like having a fraction times a whole number. We don't know whether this is a whole number or not because we don't know what kind of number y is, but we treat it kind of like that for the purposes of multiplication. That is, we think of 4y as being 4y over 1. And you can just draw it like this. You see, you can just put the line of the fraction over 1. Now, when you go through this, though, you realize that the numerators don't quite line up. You see, and the denominators don't either. But at least it illustrates where your numerators and denominators lie. Now, we're looking for cancellation opportunities, and I'm thinking about the 4 and the 12 here. 4 into 4 goes 1. 4 into 12 goes 3. And now we just multiply straight across. And don't let the letters trick you. Letters stand for numbers, and when letters are next to numbers, it means to multiply, and that's all there is to it. We don't have any cancellation opportunities here involving the letters, but no matter, we just carry them along. 7 times x times y is 7xy for the numerator. And in the denominator, 3 times 1 is 3. So this becomes our answer. Here we have an evaluation problem. Evaluate xy, which means x times y, when x has this value and y that other value. So xy means x times y. I'll put the dot for emphasis here. And the x value is 1 4/5. I'll tell you what, let's change to the improper fraction form as we bring down. 5 times 1 is 5 and 4, 9. So this is 9/5 times. Now, we have a negative value here, so rather than use a dot for the times sign, I'm going to introduce a parenthesis here to show the multiplication. And now it's negative 5/6, and away we go with the multiplying. I'm looking for cancellation opportunities, and I have one with the 5s here. The 5s just go out. 5 into 5, 1, 5 into 5, 1. I can write the 1s here for emphasis if I like. 3 into 6 goes 2. 3 into 9 goes 3. Now, positive times negative is negative, and I'm going to go out to the side this time because I'm a little jammed on space at the bottom of the board. But plus times minus is minus. 3 times 1, 3 for the numerator, and the denominator, let's see, 1 times 2 is 2. Negative 3 over 2, an improper fraction, so I'll change it to a mixed number. This is negative 2 into 3 goes 1 with 1 left over. So it's negative 1 and 1/2 for the answer. Division is related to multiplication, and we use that relationship in order to change division problems into multiplication problems. Look at this pattern. 6 divided by 2 is 3. So when we divide by 2, you see, we take 6 and divide by 2, we get 3. But we also know that 6 times 1/2, half of 6, you see, is also 3. It turns out that dividing by 2 and multiplying by 1/2 will give us the same result. And this is the idea that we're going to use when dividing with fractions, that dividing by a number is the same thing as multiplying times its reciprocal. Notice that 2 is really 2 over 1, and its reciprocal is 1/2. So dividing is the same as multiplying by the reciprocal, so we can take every division problem and change it into a multiplication problem, you see, by just multiplying by the reciprocal in order to accomplish the division. So we have 2/5 divided by 3/4. Well, we change this into a multiplication problem. It's times 4/3. We're multiplying by the reciprocal, you see, of this number. Of the divisor, and so we multiply straight across. 2 times 4, 8, 5 times 3, 15. And that's all there is to it. So we just pop it into a multiplication problem and go about the business of multiplying as we understand it to this point. Here we have negative divided by positive. We're going to get a negative result. Now, notice here that we have a 5 up here, and there's a 5 in 10. And there's a tendency here in this step that says division for us to try to cancel. That is, to cancel the 5 with the 5 factor that's in 10. But we can only cancel when we're multiplying, and we're not multiplying yet. This says divide, and when we divide, we multiply by the reciprocal. So we would rewrite this as negative 5/6 times, now flip that over, and we have 10/3. You see, now do we see a cancellation opportunity? Well, yes, but it's not with the 5 and the 10. It turns out that it's with the 6 and the 10, because they're both even, and 2 is a factor in both of them. 2 into 6 goes 3, 2 into 10, 5. And now going straight across, negative times positive is negative. 5 times 5, 25 for the numerator, and in the denominator, 3 times 3, 9. We would presumably change this to a mixed number. Let's go ahead and do that. It's negative. 9 into 25 goes 2 times. 9 times 2 is 18. And what's left over is 25 minus 18, or 7. So it's negative 2 and 7/9 for the final answer. If we want to find the quotient of 3/4 and negative 6, quotient is the answer in a division problem, and so this implies a division problem, and it's this number divided by that number. So we write it that way, 3/4 divided by negative 6. We change to a multiplication problem, 3/4 times, let's see, I better use the parenthesis here because I have a negative. So instead of using the dot, I'll open a parenthesis, and we're multiplying by the reciprocal of negative 6. Change the 6 over understood 1 to 1/6. So it's negative 1/6, and now we look for a cancellation. Oh, happy day. 3 into 3, 1, 3 into 6, 2, and we're multiplying straight across. So it's positive times negative is negative. 1 times 1, 1 for the numerator. 4 times 2, 8. So negative 1/8 is our answer. Here we're talking about mixed numbers, and with mixed numbers, remember with multiplying mixed numbers, we had to change the mixed numbers into improper fractions. And we're going to do that here as well. So really, we have 2 tasks to perform right here. One task is to change the mixed numbers into improper fractions, and the other task is to flip over this fraction. Do you think we're going to perform both of those tasks at the same time? No! We're going to separate them. We have to write 2 different steps, because if we don't, we're going to make mistakes, I promise you. So we want to rewrite as improper fractions first. 15 times 3 is 45. 45 plus 4 is 49. So here we have 49/15 divided by 10 times 2, 20, plus 1, 21/10. Now we flip over that second fraction. That is, we multiply by the reciprocal. So we have 49/15 times, flip over, 10 over 21. And now we're looking for cancellation opportunities, and we have an abundance of them. We have, let's see, 7 goes into 21 3 times, 7 into 49 goes 7 times, and 5 into 10 goes 2, 5 into 15 goes 3. Do we have other opportunities? I don't see any. 7 times 2, 14 for the numerator, 3 times 3, 9. An improper fraction. 9 goes into 14 one time with 5 left over, so 1 5/9 is our answer. Fractions could appear in any of the formulas that we've had in the past. And here's another formula that kind of begins with a fraction. A fraction is kind of built into the formula. It's the formula for finding the area of a triangle. Now, in a triangle, this is triangle ABC. In a triangle, we need to know some particular information. We need to know the length of a side, and we need to know the distance from that side to the opposite vertex. Now, each of points A, B, and C are called vertex points or vertices. And that distance from a side to an opposite vertex is called a height. Now, here we have the height from this side to that opposite vertex. And often it's the bottom side that we have information about. We have the information about the length of the bottom side, and so the height would be drawn like this. Now, it's the shortest distance from this side to that point, so there'll be an angle of 90 degrees formed right here. So we have a right angle formed here. And when I say that, let me say that again, that this is the shortest distance to the from this line to that point, and we form a right angle here. I want this distance. I don't want this distance. You see, I don't want the distance from that point on the line up to here because there's a shorter distance from the point to the line. And that shortest distance is found when that height segment forms a right angle with this side. All right, so that's the idea. Now, I mentioned that there are three sides, and therefore there would be three heights involved in a triangle. This is just one of them. So there's a side-height relationship, three of them. This side has a height related to it. This side has a height related to it. You see, it's the distance from this side to that point. But any of those will do in finding the area of a triangle. So let's find the area of this triangle. Let's say that the value B is 12 centimeters. And let's say that the height turns out to be 6 centimeters. Now, with that information, we can use our formula. Remember, we write the formula down in one step and then replace letters with numbers. So we have area is 1/2, the base is 12, and the height is 6. Now notice we introduced the parenthesis because we're changing the letters into numbers, and now we just go about the business of multiplying. We have, let's see, half of 12 is 6, and then 6 times 6 is 36. That's a way to look at it. Another way is to cancel the 2 with the 2 factor either in 12 or 6. You see, and I can show that like this. If I go all the way over here to the 6, I think of it as 6 over 1, so it's 2 into 2, 1, 2 into 6, 3. So we have 3 times 12, 36. So the area then is 36. Now the correct unit of measure, remember when dealing with area, is square measure. And we were talking about centimeters here, so we're talking about 36 square centimeters. And we can indicate that in a couple of different ways, and I'll indicate it this way. We could use cm with a little squared symbol if we want to, but I kind of prefer this. Suppose we have a 12-foot board and it's cut into pieces which are 2.5 feet long. And these 2.5 foot long pieces are going to be used as bookshelves, let's say. What is the length of the remaining piece after as many shelves as possible are cut from this 12-foot board? Now this is not a trivial problem. It's not just a very simple kind of problem where you look at the numbers here in the problem. A lot of times, you know, you see a word problem at the end of a section like this, and you just look at the numbers, and we've been talking about division, so you're just going to divide, and that's going to give you your answer. Well, there's a little more to this problem than just doing that. We have to really think our way through it here. We're starting with a 12-foot board, and we're cutting pieces that are 2.5 feet long. So it's kind of like we have a board like this. You see, and let's say this is 12 feet, and we cut off a piece, and so there we have a shelf, and then we cut off another one, and we have another shelf, and we cut off another one, and we have another shelf. And when we cut as many as we can, then we want to find out what's left over. Now, this is certainly not to scale. I'm not implying here that we have a lot of these or very few. I don't know how many we have, but here's how we find out how many we have. We want to know how many of these 2.5 foot lengths there are in 12 feet. That is, how many times will 2.5 go into 12? Or another way to say it is, what is 12 divided by 2.5? That'll tell us how many times 2.5 goes into this. So that's the idea, and I've mentioned it 2 or 3 different ways. There are a lot of ways to look at this correctly. So to find out how many of these 2.5-foot units there are in this 12-foot board, we divide. We take 12 and divide by the 2.5. So it's 12 divided by 2.5. And our answer will be the number of these rascals there are in that. You see, how many of these are in there? That's what we're finding out here. Now, so this is 12 over 1. And now I'm changing to the improper fraction form. 2 times 2, 4, plus 1, 5. So this is 5 halves. Now we change to the multiplication problem. We go from division to multiplication by flipping this divisor, by multiplying by the reciprocal. Okay, so this becomes 2/5. And away we go with the multiplication. 12 times 2, 24, and 1 times 5, 5 for the denominator. Now we need a mixed number here out of this improper fraction. 5 into 24 goes 4 times. 4 times 5 would be 20. And so we have 4 left over. So 5 into 24 goes 4 whole times with 4 left over. 4 and 4/5 then is the result. So what this means is that we can cut 4 and 4/5 shelves out of that 12-foot board. So when we cut off this 4 whole shelves, we have 4/5 of a shelf left. Now, I want to emphasize that and interpret it that way because it's not like we have 4/5 of a foot left, which is what we might tend to think here. It is that we are determining here, the number that we have here is the number of these 2.5-foot length shelves that we have in that 12-foot board. And what we can do is cut off 4 whole shelves, and what we have left is a length which is 4/5 of a shelf. Okay, now to find out how much board is left, we have to determine what 4/5 of a shelf is. How long is 4/5 of a shelf? Well, each shelf is 2.5 feet long. So 4/5 of a shelf is what's left over. 4/5 of 2.5 means 4/5 times 2.5. So it's 4/5 times 2.5. 2.5 is 5 halves, and away we go with multiplication. Now notice it's a multiplication problem. It's not a division problem. We don't have to flip over. So we're looking for cancellations. 5 and a 5, 1. 5 and a 5, 1. The 2 and the 4 cancel. 2 and 2, 1. 2 and a 4, 2. Multiplying straight across, we have, let's see, 2 times 1, 2 for the numerator, 1 times 1, 1 for the denominator. 2 over 1 is 2. So the remaining piece is 2 feet long.